in class, gave common base a try, the RN for a common base. And first you had to figure out what a common base looks like. And a common base is a good friend of common emitter, except in the common emitter, the emitter isn't moving and the base moves, but in a common base, the base doesn't move and the emitter moves. So it's just switching which is the input. So I can call that a V bias, and it's a V out. We'll just call that R. Okay, so first step is to draw a small signal, to replace the transistor with a small signal model so we can figure out how much things are moving, not just what the voltages and currents are, but how much things are moving. RO, and then we have V in here, and this is V bias, but V bias is a DC voltage, so this just ends up being grounded. And then we have R going to the supply voltage, but because the supply voltage is DC, that goes to ground. And then we also have V out on the collector. Okay, in this case, there is nothing we combine. This R pi goes from ground to Vn. There's nothing else that goes from ground to Vn. RO, you might, at first glance, it might look like it goes to Vn, and since we're used to grounding stuff, you might think that RO and R pi are in parallel, or R and RO is in parallel, but remember, RO from V out to ground, RO goes from V out to Vn, so those aren't in parallel, and then R pi goes from VB to Vn. Okay, so there's nothing to simplify here. We're trying to find Rn, so we have to figure out what exactly we're trying to find. And that's going to be Vn, which is already on your diagram, and In, which isn't on your diagram. So we need to identify where that is. And whenever you have an In, it's always into the circuit. The only time you have to worry about the direction of the current, it's always into the circuit, except for GM when you have I out, and that's going out of the circuit. So R out is also into the circuit. Okay, since there's nothing to simplify, and it's really hard to see where the best place to start is, I always go to this equation and look for a current. So I see I in. And I in is this current right here, and so it's the sum of this current, and this current. So it's the sum of Vn over R pi. So In's going into this, and that equals the current out of that node, minus Gm VBE, and current through here, which is V in minus V out all over RO. Okay, so we've got to start here. Any voltage or current that shows up in here, we get to leave that. And so I see I in this equation, V in, oh, VBE can't be there. So this one's, we need to replace. V in's in that equation, so keep that. V out's not in that equation, so that one needs to be replaced. So let's look at VBE first. It helps me to keep track of where VBE is in my circuit. So that's VBE, and I see base is 0. The emitter is V in, so it's 0 minus V in. So VBE just equals minus V in. So if we replace that, that's great, because now Vn is something we see in the Rn equation. So this term is actually done. This just goes to minus Vn. So I guess we'll might as well update as we go. So we have In equals Vn over R pi. And then since this is minus Vn, this turns into a plus Gm Vn plus Vn over Ro minus V out over Ro. Okay, so now we need an equation with V out in it. And what we want to do is we want to replace V out with an equation made up of Vn and In. So our goal is to get this entire equation with only Vn and In, no other voltages or currents other than Vn and In. So we need to replace V out with a function of, we need V out to be a function of only In and Vn. Any other voltages or currents we need to get rid of. So we need V out in the equation because we want to massage it so it V out equals something. And bring the picture down. So right here. So we need an equation with V out in it. And I'm just going to go for another KCL at this node, which means that I have negative V out over R. So that's the current going through here. It goes from 0 to V out. So 0 minus V out is negative V out over R. And then I have plus V in minus V out over RO. And then we have negative GM VBE. But we figured out that VBE equals negative Vn, so I can just change that to that. So now we have the current through R and the current plus the current through in opposite direction through the current dependent current source and the current across RO, that all should sum to 0. And let's check this equation out. We have an equation with just V-ins and V-outs, and that's good because we need when we pull V out over to one side of the equal sign, we want the stuff on the other side of the equal sign to only have In and Vn, and this would only have Vn, so that satisfies this function. So let's do that. Let's move V out over R plus V out over RO. GM V in, and then we also have this V in, so that's plus V in over RO. So let's check out our signs. So when I move this over, this turns into a plus. When I move this over, it turns into a plus. This leaves V in over RO and GM V in. So I think that's good. But what we need is V out equals something. So I'm going to factor out V out here, and that's going to equal a GM V in plus V in over RO all over 1 over R plus 1 over RO. So now we have our equation for V out. And let's remind ourselves of the equation that we're going to put it into. This one, a little better on that one. Okay, so that's the equation. Let's see if I can shrink it. It's still being readable. Kinda. Okay. So there's our equation, or now we now have V out for. So now we have to put V out into this thing. So we have, oh, this is interesting. There's only one I in, unless I messed up my math, which is very possible. Plus GM V in plus V in over RO minus V out, which is this whole thing, divided by RO. So okay, we're trying to find our in, so it needs to be V in over I in. Factor out this whole thing, factor out V in from every single term in this whole thing, and you have I in on that side. So what you end up with is V in over I in equals 1 over R pi plus G in plus 1 over RO minus 1 over RO times Gn plus 1 over RO. All the units seem like they're working out here. 1 over R plus 1 over RO. There's probably something I could have done to make this prettier. But yeah, if I asked you on an exam, I'd probably accept this right here. Got this RO right here that we can multiply through, and you end up with RO over R plus 1. Let's see, if I was going to, just as an extra step, this is, you know, a spreadsheet. If you have an equation like this, and you're changing values of currents and all that, spreadsheets are great, great to use. If I multiplied the RO through, well, how about this? Let's do this a little differently. Assuming 1 over RO is going to be much smaller, I don't want to just say, oh, this is 0 and get rid of this. But I'm going to do, I often, if I am not sure if getting rid of things will mess up the answer, I often go step at a time, and RO is usually just the most gigantic. So I would get rid of this 1 over RO, but I'd multiply this RO through, so I'd get GM plus 1 over RO all over RO for R plus 1. If I wanted to go yet another step, I'd assume 1 over RO is much less than GM, so I'd have a 1 over my 1 over R pi. I'm not saying to do this, but just if you were going through the simulation, the simplification steps, I'd probably call that GM R over RO. I'd say this 1 is much less than R over R. 1 over RO is much smaller than GM. And then if I really wanted to go on from there, I think I'd stop here. But yeah, so if I asked you not to simplify things, this would be your answer up here. Sorry, I kept rambling after we got to the actual answer.